Hello, this is the Section 2.3 lesson. In Section 2.2 we introduced the idea of random variables and distributions, and we introduced one specific type of distribution, the simplest of all, called the uniform distribution. In this section we're going to introduce two more specific distributions we call the hypergeometric and binomial distributions. These distributions apply to random experiments that meet certain requirements. So let's define our first type of distribution called the hypergeometric. So consider a random experiment that meets the following two requirements. Number one, we select n objects from a population of capital N without replacement. And then number two, the capital N objects are of two types. Call them type 1 and type 2, where capital N1 are of type 1 and capital N2 are of type 2, and of course N1 plus N2 has to equal capital N. Okay. So we're only dealing with a random experiment that meets these requirements. We're selecting some objects from a larger group without replacement. Notice the emphasis there on without replacement, and we have two types of objects. Okay. So we're going to define the random variable capital X to equal the number of type 1 objects in our sample of little n. Okay. So then X has a so-called hypergeometric distribution, and its probability mass function is given by this. So little f of x is, by definition, the probability that capital X equals little x, and we can calculate it using this formula here. And so these are all combinations. It's a combination times a combination divided by a combination. And our values of x can go anywhere between 0 and little n. Obviously, in a sample of little n, you can't have a negative number of type 1 objects, and you can't have any more than little n type 1 objects. Okay. Now, these numbers, capital N, little n, N1 and N2 are called the parameters of the random variable. And that's a term that we're going to be using frequently throughout the rest of the semester. A parameter is simply a constant that's used to identify or that's used within the distribution or the probability mass function. So to illustrate this, let's look at this simple example. A manufacturer of radios receives a shipment of 200 transistors, 4 of which are defective. To determine if they will accept the shipment, they randomly select 10 transistors and test each. If there is more than one defective transistor in the sample, they reject the entire shipment. Find the probability that the shipment is not rejected. Okay? So notice what we got here. We got a large group of objects, in this case 200 transistors. We have two types, defective and not defective. 4 of them are defective, 196 are not defective. And we are going to select 10 transistors, and we'll do that without replacement because we're not going to test the same one twice. And we want to know something about the probability of a certain number of defective transistors. So we're dealing with a hypergeometric distribution. Okay. And so first of all, let's define our random variable. Capital X is the number of defective transistors in the sample of 10. That's what we're really interested in, the number of defectives in our sample. Okay. So then X is a hypergeometric distribution. We've already identified that. Now we need to identify the value of its parameters. Well, capital N is the total number of transistors, that's 200. Little n is the number that we are selecting, that's 10. N1 is the number of type 1 objects. Well, a type 1 object in this case is a defective transistor because that's what we're interested in. And we have 4 of those. And then N2 is the number of non-defective transistors, which is 196. So now we know what type of distribution we're dealing with, and we know the values of its parameters, and so now we can use those numbers to calculate our probability. So we want to know the probability that the shipment is not rejected. That's the question that's being asked. So now we think about what does that mean in terms of our random variable. Well, it's not rejected if we have 0 defectives in our sample or 1 defective in our sample. So we want to know the probability that x equals 0 or x equals 1. And so in terms of our PMF, we simply need to calculate f of 0 and f of 1 and add those two together. And so we plug in the values of our parameters, the values of x, into our PMF as shown there. And then we do that arithmetic on our calculator. We get those numbers, add them together, and we get our probability of 0.986. So there's about a 98.6% chance that our shipment will not be rejected. Now, before we define our next type of distribution, we're going to define something that we call a Bernoulli experiment. So a random experiment is called a Bernoulli experiment if each outcome is classified into exactly one of two distinct categories. And this is the key word here, two distinct categories is the important phrase. To have two distinct categories to be a Bernoulli experiment. Now these two categories are commonly called success and failure. Success does not necessarily mean that something good happened, nor does failure mean that something bad happened. Success is a generic term for meaning that we observed whatever it is we're interested in. Now, continuing on with this definition, if a Bernoulli experiment is repeated several times, so we do it over and over again, in such a way that the probability of a success does not change from one iteration to the next, the experiments are said to be independent. So if we do it over and over again, the probability of a success does not change from one time to the next, and we say that the experiments are independent. Okay. Now, a sequence of n Bernoulli trials is by definition a sequence of n independent Bernoulli experiments. Okay, so this is kind of a technical definition. N Bernoulli trials means that we repeat something over and over again, and the probability of a success does not change from one to another. An example might be like flipping a coin. We flip a coin, we're either going to get heads or tails. If we consider tails a success, the probability of a success doesn't change from one trial to the next. So flipping a coin a bunch of times would be a sequence of n Bernoulli trials. Now, we're going to use this idea of Bernoulli trials to define our binomial distribution. Okay? So consider a random experiment that meets these two requirements. So a sequence of n Bernoulli trials is performed, and the probability of a success on any one trial is p. So we're going to perform something over and over again, and we're going to let p denote the probability of a success on any one trial. Now define the random variable x to be the number of successes in the n trials. So in this definition, we're interested in the number of successes. So then x is said to have a binomial distribution, and its probability mass function is given by this. Little f of x, by definition, is the probability capital X equals little x. It's equal to n choose x times p raised to the x power times 1 minus p raised to the n minus x. And here our random variable can take on values from 0 up to n. We can't have a negative number of successes, nor can we have more than n successes in n trials. Okay. Now this type of distribution has two parameters, n and p, and the phrase x is b of n comma p means that the variable x has a binomial distribution with parameters n and p. So we're going to see this phrase come up a lot throughout the rest of the semester. So b stands for binomial. The first number is the value of n. The second number is the value of p. So let's do an example to illustrate an application of the binomial distribution. So if a family with 9 children is randomly selected, find the probability of selecting a family with exactly 4 boys. Okay. So let's define the random variable x to be the number of boys in the family, because that's what we're interested in. Okay. Now, the next is to observe that x has a binomial distribution with 9 trials and a probability of a success of 0.5. Now how do we know that? Well, think of each child in the family as like a trial. It's either male or female, boy or girl. And a success here is a boy because that's what we're interested in. And we're going to assume that the probability of a success is 0.5. So each one of our 9 children is a Bernoulli experiment. We have 9 trials, probability of success is 0.5, so we're dealing with a binomial distribution. Okay. So now once we've identified that, we can easily calculate our probability. We want to know the probability of exactly 4 boys, so we need to calculate f of 4. We plug things into our PMF, and we get our answer of 0.246. So what that means in a practical sense is that about 24.6% of all families with 9 children are going to have exactly 4 boys. Okay. Now these two distributions are very similar, and sometimes it's difficult to determine which type of distribution we're dealing with. So let's just kind of summarize these two distributions. So in a hypergeometric distribution, we are selecting items without replacement. And we have 2 types of items, and we want to know the probability of a certain number of one type. Okay. But in a binomial distribution, we're not selecting items. We are repeating independent trials. We're doing something over and over again, and the probability of a success does not change. Now we have 2 categories of outcomes. Not 2 types of items, but 2 categories of outcomes. And we want to know the probability of a certain number of successes. And so again, these 2 types of distributions are similar. To determine which one to use, ask yourself, am I selecting items or am I repeating independent trials? If I'm selecting items, then it's a hypergeometric. If we're repeating independent trials, then it's a binomial distribution.